Okay, so this is based on the first review multiple choice packet that you gave me questions on. So I'll go through those questions. We're going to start with question number 1. So here there are particle diagrams. They tell you that you have equal amounts of X and Z2, so equal moles or molecules, and they don't tell you how much it is. You'll notice that they specifically tell you it is an unbalanced reaction. Hopefully you noticed that anyway. You can balance it, but you don't necessarily have to. The first thing I'm going to do is, if I have equal moles or equal molecules, I know for every one X, I must have 2 Z's, right? Because it's X and then Z2. So I would go through and count the X's and Z's in each picture. You need to have a 1-to-2 ratio. So no matter how they are configured in terms of molecules and single particles or whatever, you have to have twice as many white dots as you do shaded ones. So if you look at A, you have 4 shaded ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 white dots. So it cannot be A, because if you have 4 shaded dots, you need to have 8 white dots. So let's look at B. 1, 2, 3, 4, 5 shaded, so we would expect 10 white ones. And that is how many we have, so that's an option. For C, we have 4 shaded, so we would expect 8, and we have 10 whites, so that doesn't work. And then for D, we have 4 shaded, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 white ones, so again, that doesn't work. So right off the bat, I automatically know it has to be B. So, like I said before, it is an unbalanced reaction. You don't even really need to balance it if you don't want to. Okay? Now, because this is helping you prepare for the test, what I'm going to do next is tell you, okay, what if that counting business hadn't worked? What if it wasn't that easy? Okay, if it wasn't that easy, then you should look, next thing I would do is look at limiting reagent, which of course you do need to balance for. So we would have a 10 here and a 4 here. You could also use mixed numbers, that's fine. It doesn't, yeah, it's up to you. Okay? All right. So if we do see it as limiting reagent, you would say, like, okay, which one is going to be left over if you have equal amounts? And we don't know how much that is, so this goes into one of those situations where you can just kind of pick what you want. Okay, so say we had 10 moles or 10 molecules. That's easy number, 10. Okay, so say you have 10 moles of X and 10 moles of Z squared. The next thing you would do is divide by the coefficient. So you would divide by 4 here and 10 here. Clearly, the limiting reagent is going to be Z2. So you could eliminate any that have Z2 left over. Okay, so automatically, and this is again pretending we couldn't get B right away, automatically A would be gone because it has Z2 left over, and D would be gone because it has Z2 left over. You also could get rid of anything that does not have X left over because X is an excess reagent. Just because we have equal molecules doesn't mean they're both completely used up, okay? Hopefully you did notice that. So in that situation, we could get rid of C because it does not have any X left over. So again, we arrive at the answer of B. Okay, so that's two ways to solve this same problem. All right, so that brings us to number 2. For number 2, it says these made up elements are in different compounds. What has the same empirical formula as dihexene hexaziamide? It's made up, so I don't know how to pronounce it. But I will say I can write the formula here, X2Z6, because I know di is 2 and hexa is 6. That's, of course, a molecular formula because it's not reduced. So we know the empirical formula is going to be XZ3. So we are looking for which one of these samples has the empirical formula XZ3. Now, you can do most of this in your head. I'm going to do it out for purposes of teaching, but hopefully you wouldn't spend this much time on this multiple choice question. You know, to find the empirical formula, you take the mass, divide by the molar mass. That gives you the moles, and then you divide by the smallest moles to find the subscript. So for A, for X, you're going to take 32 grams, divide by the molar mass of 8, and that gives you 4 moles of X. And then for Z, you have 20 grams, divide by the molar mass of 2.5, and that will give you 8 moles of Z. When you divide by the smallest moles, you get X1, Z2. That is not our XZ3, so we can get rid of A. Okay, now you just do the same thing for all of these. Again, hopefully you can do a little bit of this in your head so it doesn't take you this long. So here we would have, for X, you have 40 over 8. For Z, you have 25 over 2.5. So that gives you 5 for X and 10 for Z. When you divide by by 5 here, you get XZ2 again. So get rid of B. For C, we have 8 divided by 8. So that gives us 1 for X. 7.5 divided by 2.5 gives us 3 for Z. And that gives us X1Z3, which is the empirical formula we're looking for. So that's going to be the answer. And just to be safe, because I do have time, I'm not taking a test right now, I'll do D. We have 16 over 8 gives us 2 for X. 12.5 over 5 gives us 5 for Z. Divide by 2, and you get X1, Z 2.5. You know you can't have those decimals or subscripts, so you would change that to X2, Z5. Not what we would want, so not the right answer. So the answer must be C. Okay, 3. Now, for number 3, I ignored the melting point when I solved this one because, quite frankly, it's hard for you to tell if those are technically high or technically low. It would have been better if they had told you high or low. I mean, it would have been easier, I should say. So I ignored the melting point and just looked at the conductivity. So if I start with X, there's no conductivity in the solid phase and none in the liquid phase, which means it cannot be a metal or an ionic compound, because a metal would have conductivity in the solid phase, an ionic compound would have it in the liquid phase when it's molten. So I'm going to get rid of C and D right away because sodium chloride and silver. Okay? Now, I'm sure the melting points could help me determine between glass and graphite, but I don't know enough about that. So I'm not going to focus on that. I don't think that many of us do. I think we do understand conductivity because that's something we go over quite a bit. I don't think that many of us understand the melting point situation without an IMF, whatever, in comparison. Anyway, so now if we go on to why, it says that there's high conductivity in both solid phase and liquid phase. Gold could definitely be a possibility. Phosphorus, probably not, because phosphorus is going to be, it's going to be kind of covalently bonded. I don't want to say that too much because it's like, it's a solid, but it's going to be not an ion, even when we put it in the liquid phase. But just to be safe, we'll look at Z. When there is no conductivity in the solid phase, but there is in the liquid phase, it has to be an ionic salt. It has to be. That's the only thing that does that. So that means potassium iodide will work. Okay, so the answer has to be A. So now we'll go to question 5. Okay, for number 5, I'm going to start by eliminating 2 of them right off the bat. A is the opposite of what we know to happen. If we had less frequent collisions with the walls of the container, that means pressure is going down. That's the definition of pressure, collisions with the walls of the container. You know from first year that when pressure goes down, volume goes up. A says the volume is less, completely contradictory to what we know is true. B pretty much says that we can never use 22.4, and we do know from our notes that there's plenty of times when we can use 22.4. So that brings us between C and D. And for this one, I think you just need to use your gut. NH3 has hydrogen bonding, right? Because it's hydrogen connected to NO or F. So hydrogen bonding is a pretty strong attraction. This makes sense. D makes sense to me because it's saying they're attracted to each other. So it decreases the space. C is saying, okay, but we have a high enough pressure and a low enough temperature to overcome that. So what C is talking about is this ratio, which if you look at your notes for a gas, that ratio needs to be over 1 for ideal gas behavior to work. I don't think that based on our attraction, we're going to have a high enough pressure and a low enough temperature to overcome that at STP. So to me, the best answer is D. And that's just using your gut, saying, like, I know hydrogen bonding is really strong. And so in order to overcome those attractions to each other, I'm going to need more than STP. That brings us to 11. All right, so we have percent distribution, Ka. This is just an x squared problem because it's not a titration. It's just a solution of HA. Our molarity of HA is 2. And our Ka is 8 times 10 to the negative 4. So when we solve for x, we get this. So the concentration of either A minus or H3O plus is going to be this. Okay. However, that's obviously not the percent dissociation because you have to start off, you have to take the percent of HA that you started with. Or excuse me, the amount of HA that you started with. This is the amount of HA that's dissociated because that's the amount we have of this. So now to figure out what percent that is, we need to put it over the percent we started with, which was 2. Let's put that over 2, multiply by 100 for percent, and you get 2%. All right, number 15. Okay, reverse reaction. So in this question, 14 starts it off. In this question, they're saying you start with the liquid and go to the gas. So the reverse reaction, oops, is going to be going from the gas to the liquid. So we know that Kp is going to be the pressure of the products over the pressure of the reactants. The product is a liquid, so that's not going to be any pressure, right? So we're going to put 1 over the pressure of our gas here. What's the pressure of our gas under all the same conditions? Meaning it goes to equilibrium and everything. This. It's because no matter what you start with, whether you start with the liquid or the gas, the equilibrium pressure is going to be the same. So put 1 over, and you get 5D. So that's just counting on you knowing that no matter what you start with, the products or the reactants, you're going to end up at the same pressure at equilibrium. All right, that brings us to 19. Coulomb's law. Okay, this is just a quick, it needs to be charge over distance squared, or charge over distance if you want to think of it that way. You can completely ignore the K here. You don't need to have this formula written down. Obviously, it's multiple choice. So I'm just going to think of this as charge over distance. Okay. Now, I also will want to say a key thing in here is most likely. Okay, because we know that there could be things that factor in here, and most likely you want to pick the one that has the higher charge and the lower distance. Higher charge, lower distance, B. Because we have a 2. Remember that charge in this case, it could be positive or positive or negative. So you want to take the absolute value if you're thinking of it as just charge. And then, so I would be deciding between these two because I would look at the charge first, pick the one with the smaller one. Okay. Also, I think you only really want to, like, these distances are pretty close. So I don't even really think you need to worry about that, trying to compare all 4 of them. All 4 of them, because those distances are pretty close. I think you can get rid of the 1 minus charge right away and just compare the 2 minus charges. Next question was 21. We've done problems like this. We might have even done this exact problem. I think there are 2 places where you might get caught up. So the first thing I'm going to do is write down the moles of each thing that I have. And then that's going to give me, because it's a 1-to-1 to 1 ratio, we don't really care about that. We're talking about precipitation. That's going to give me this many moles of the precipitate. Okay. Next thing I'm going to do is find out what the Q is. So they tell us it's 20 grams, C is 4, and the difference, delta T, is -2. So that comes out to negative 160 joules, which is negative 0.16 kilojoules. But keep in mind, and this is the first place I think people might get hung up, that's not for mole of reaction. That's for this, 0.002. So in order to get the mole of reaction, you need to divide by the moles that it is for, and then that gives you negative 80 kilojoules per mole. Okay, so we can automatically get rid of these two. Now, I think a lot of you probably picked A, but you have to keep in mind, and this is something I talk about a lot in first year, that whenever you're seeing a temperature taken with a thermometer, that is the temperature of the surroundings, not the actual system, not the actual reaction. Now, this goes into Q equals negative Q, whatever. This is Q of surroundings, because that's where our delta T comes from. Okay, so Q of the system is going to be the same thing with a different sign. So the answer is D. Keep that in mind. Whenever you see a temperature that's taken in a lab, it is the temperature of the surroundings. The only time you'll really have like a change in temp of a system is when they give you a PE diagram, or they give you a chart where it says that's the difference in PE, something like that. But if it's a temperature, it's the surroundings. All right, 24. I thought we had one before that. Oh no, okay. All right, 24. Okay, 24, keep in mind that this is before calculators were allowed, okay? So you could probably figure out what the pH actually is. This is asking you for the approximate pH in the Na3PO4 solution. Yeah, I think it's a pretty easy question based on that, quite honestly. I don't even think you need the Kas. So what they're asking you for is the pH based on the Na3PO4 solution. So they're just saying when Na3PO4 was put in water, because it's an Na, you know it's going to separate. This is pathetic. So you know that because this is a negative ion, it's going to be basic, because all negative ions are basic, unless they're also pathetics, which this is not. There's only one choice for a basic pH here, D. Now again, you might be able to figure it out based on the 3 Kas and do all the math out, but you don't even need to. It's not even necessary. Yeah, same deal here, actually. 31. This was a pre-calculator question, so it's your best estimate kind of thing. We can do out the math. This one's actually really not hard, so I might do out the math, but we're going to have a strong acid and a strong base. They're going to give us H2O and a salt. Okay? Now, if we had equal amounts, equal moles, then it would be neutral because it's strong acid, strong base. We don't, though. We have we have these two left over. So we're going to have some acid left over, which means we only have one option. Now, if they did on a calculator thing, if they wanted you to find the exact pH, now that you have calculators, you could take the amount of acid that's left over, put it over the volume, combining them, 75 plus 150, and then take the negative log of that, and your pH would be 1.88. So, I mean, the better answer would be closer to 2, but 3 is fine. It's the only acidic pH there, so you have to pick that one. And it does say which is closest to which of the following. "35 I thought was an interesting question. It's definitely not A or B. Because we know that a reaction being exothermic or the entropy change is negative. It's just part of the story. Okay, we know that that doesn't really tell you whether reaction is going to happen or not. But between C and D, because they use the word spark, it's not really changing the temperature, right? If we heated it up, like with a Bunsen burner or a hot plate or something like that, that's changing the overall temperature. In both of those situations, we are adding energy. But a spark is really just going to get to the activation energy really quickly. It's not going to change the overall reaction. I should say the overall delta G. It's just going to get that activation energy up. So that's why the answer is C. I can see why people would pick D. But it's just think of the flame test that you did first year, most of you. If you It's not like we changed the temperature of the surroundings. We just put the thing in a flame and got it to be activated. It's not the same. But we used a spark. Okay? If we were heating up a beaker with that Bunsen burner, that would be changing the temperature of the whole thing. We're not doing that. We're just giving it the energy it needs. So that is why the answer is C, because a spark is just giving it that energy. It's not changing the delta G system, which is what D is getting at, right? Thermodynamically favorable. Next one you asked about was 41. All right, for 41, I would get rid of D right away. You don't need HCl because HCl is in all three of them. So we don't have to worry about that. So what we're going to look at is when these bonds were formed, because that's what's happening over here. And that's what's happening overall. Because, for example, here you have two NH bonds being broken, but three being formed. So overall, one was formed, and that's true for all of them. Overall, in the first one OH was formed, then one NH, then one CH in the last one. Okay, so we're going to be looking for a bond that was formed. Now, when a bond is formed, that releases energy. Okay, so for delta H, for just that one bond being formed, it's going to be negative. Okay, so what you're looking for here is, okay, which one of these is, I guess I'll start with strongest. Which one is so strong that it overcame all the bonds breaking? The bonds breaking would be positive, the bonds forming would be negative. Okay, so you can see right away that the first one has a negative delta H. So this was super strong. Okay, it was so strong it overcame this breaking and this breaking. All right, so that's super strong. We are looking for the weakest, so we're getting rid of OH right away. Super strong if it's negative. Okay? By that same logic, right? Just because these are both positive doesn't mean we can't compare the relative strength. If you want to think of it, positive 14 is more negative than positive 36. So this would be the next strongest because it's more negative than 36. So the answer for the weakest one is going to be B. All right, last question. And I had this question last year too, and I totally get it because you have to use common knowledge, common sense. And it's really hard to think about that when you are in the trenches of an AP chemistry exam. Okay, so the first thing I can do is eliminate 2 right away. Because one thing that hopefully you noticed is that you have 3 moles of gas here and 2 here. So delta S is positive. So we'll get rid of A and C. Okay, now between B and D, if you look and you want to do out the delta G formula, they're both possible. You can have a negative delta H and a positive delta S, and delta G could be negative depending on the temperature, which we don't have information about. For D, you could have positive delta H and positive delta S, and you could have a positive delta G, again, depending on the temperature, okay? So both of them are possible. So then you kind of get stuck in this like, but I don't know how to figure this out. And that's where your common sense comes in. Look at what the reaction is telling you. It is telling you that H2O gas is splitting up into H2 gas and O2 gas. It is telling you that that happens at 25 degrees Celsius, which is essentially room temperature. It's like 70-ish degrees. We have water vapor all over the place. You know that. Okay, you know that. You know that when it's 70 degrees, all the water vapor doesn't start splitting up into H2 and O2. We still have water vapor. So that's not a spontaneous process, right? There'd have to be something else going on there. It's not spontaneous, which means delta G needs to be positive. And that's why the answer is D. Okay? So when they ask this question, I think they are trying to get at whether you know that delta G being positive is not spontaneous, but it's just not as clear unless you take a step back and you're like, okay, I know all this chemistry, but what else do I know? You have common sense in there too. So use that as well.